better.
Recording?
Okay.
Okay. All right, well, here we are, Gary.
Well, I'm glad we finally got around to doing this.
Yes. Yeah, this is an opportunity for us to, we have found that experience has significant depth, like an iceberg. There's much more beyond what you see on the surface. So we're hoping to dig a little bit into the deeper side of engineering by tapping into your experience and giving you an opportunity to tell some stories.
Well, there's a lot of them. I'll mention a few simpler ones to start with. But throughout my career, very frequently, the most interesting thing about engineering is when your boss comes to you and gives you some impossible project, or it seems that way at the time, and they give you the usual just a few days to get it done. So that's what you work up to as an engineer. You'll find out pretty quickly. However, to get there, I think often you need to start with very simple views of things. And I like, when I'm working with young people, start working with young people, and of course I've done a lot of work in programming. And I like to start the engage a discussion over simple things where we both know what we're talking about. Yeah, it is not quite, even simple things are not what they seem to be. So one of the first things I like to do, and this gets the discussion going, is to ask a young engineer, well, do you know what the working principle of a coffee cup is? Now that's kind of an obscure way of saying it, but then what I go on to say is that a coffee cup has glaze on it. And what's the purpose of the glaze? What does the glaze do? We all know this, but the question is, like the iceberg, how important is that glaze? Well, this kind of stumps most individuals, and they think it keeps the liquid out and it makes it easier to clean. It's prettier aesthetically, etc. But that's not really any part of the important reason for the glaze. A coffee cup is made of clay usually, and without the glaze, the coffee cup is porous. However, it's also very weak. So the coffee cup, if you were to drop them on the floor, they don't often break if you get right down to it. Maybe about 1 out of 3 or 4 or 5 times they break. But usually they don't break. But if you drop a unglazed coffee cup to the floor, it breaks immediately. The reason is that unfired clay, we know breaks quickly, but even fired clay tends to break. And the glaze actually forms a skin on the coffee cup, and that skin, it's applied and then it's heated, and then it shrinks when you bring it out of the kiln. That shrinking of that skin makes a very tight coating, and that coating actually holds the coffee cup together and prevents cracks from propagating, and you can drop it usually and the coffee cup really won't break. So that's what I would call the working principle of a coffee cup.
Yeah, and you often ask, what do you think actually makes a coffee cup strong? And oftentimes people will say, the clay. But we know now that the compressive force of the glaze squeezing the clay together is what makes it strong.
That's right, and even that is not obvious and require a materials science course and some advanced math to more fully explain it. But that's where I like to start, because very frequently we think that simple things around us can, in effect, be taken for granted. And we know that for example, with our car, things like changing the oil, this may seem like a simple thing, but it has very big consequences if you don't change the oil. And so these simple things like the coffee cup, and there are other things I like to use, because some people might think, well, a brick, what's the working principle of a brick? And I would say, well, yeah, right, what is the working principle of a brick? It's not obvious. Once again, you take the brick and you drop it. Frequently they will actually break, depending on what they fall in. A brick is not particularly strong. It has no glaze on it. So but we know the brick holds up an enormous weight. If you look at a building, a multi-story building with brick facade, the brick may go up 50, 60 feet, and well, what's going on here? turns out the brick made up of fired clay actually gets stronger under compression. So if you were to take a sledgehammer to the brick, we know that the sledgehammer on the brick laying on the ground, let's say, would shatter immediately. But if you take that same sledgehammer, or a bigger one, and you hit it to the bottom of a brick wall, you will find you barely even leave an impression in the brick, if anything at all. You certainly won't crack it or break it. I actually did this once. That's where I learned about this. I'm an electrical engineer, and I learned quickly about how actually the cinder blocks in this case were. So, and there are other things like this. And I think that if we look at the world around us, and we see and are inspired by what seemingly is the simplicity of things, yet we didn't really understand. And this is what the word understanding means. Deep, insightful, profound understanding. We now know more about a coffee cup. We know more about bricks. One of my favorites is a rope. And the reason it's my favorite is because it's more complicated than the coffee cup, and it also has a number of analogies. And the essence of engineering, it really is the application of analogy in many ways. But in this case, just looking at a rope, we say, well, what's the working principle of a rope? And we're talking about a real rope, a rope made of hemp like they used to use on a sailing vessel. You don't hear much about hemp ropes anymore, but they're there. And the hemp has a fiber, I don't know, 5, 6, 8 inches long at the most, and these are woven together in terms of multiple braids or strands. I don't know the words for that. And then each of these are then woven together. So if you actually look at a hemp rope, there's 3 or 4 layers of the rope woven into these helixes or spirals. And then finally when you get the rope, and the actual, you wonder, well, why do the fibers not pull apart? And well, the reason for it is as you pull on the rope, these fibers, which are twisted around each other, when you pull on them, the rope kind of shrinks a bit and the fibers become closer together. And as they get close together, there's a higher coefficient of friction, or at least the coefficient of friction has greater force, so that the fibers can't pull apart from each other because they're held together, and the twisting of the rope actually is an exponential force, is an exponent there, which you pick up in your first year of physics. That rope around the tree model is what's used. So that as you pull on the rope gets stronger and stronger, and none of the fibers break when you pull on a rope. Whereas if you were to actually look at any of the individual fibers, and we were to somehow arrange them in a linear array and pull on them, they would break individually, but they become immensely strong when they're woven together.
So we have the working principle of the ceramic coffee cup, the clay brick, the hemp rope. And we're seeing that there's more going on here than meets the eye initially, but then there are also these analogies that we can draw from them.
And glad you reminded me there. The analogy of the rope is that if we build a team, the human beings have different strengths and weaknesses, kind of like the hemp fibers. If we build a team properly, have roles and are properly trained, and observe the nature of, let's say if it's an athletic activity, the rules of the game, then the team can pull together. How do those words work? Well, they work nicely in the rope, and they work well in the team. So the team pulls together, and the team becomes stronger to the extent that the different members play off each other's strengths and avoid each other's weaknesses. So that's the analogy I like, and when we build a team, and in programming, this is one of the more difficult things to do, but not impossible. And in fact, I think that programmers, because of their interaction with a common code set, they actually have more opportunity to interact with the products of their work and of their skill sets than most engineers, because engineers may work in different parts of the building, and there's not necessarily any sharing of the physical structures. But the code, because of those fibers of the rope, we can actually see how each of us are doing, how well we're following coding standards, and how well the code reads. We can see this in each other, and we can then pull together, and as we work together, we can share information about how to code better. And so, actually, ironically, often software, which people may think is more difficult for people to work together, there are opportunities for us to work together. And that, in the company Augment, of course, that's what we're trying to do. We're trying to find ways of pulling together, making it easy, and building very strong teams, even though they're distributed. So that's why I like talking about the rope analogy.
Yeah, and of course, we're spanning now from the essential elements of engineering and engineering principles applied to then software, and engineering principles applied in a collaborative environment. So this really lays the foundation for almost all of our future conversations, specifically about Augment, the company, and the training program. Because these are the three things: engineering, collaboration, applied to software.
That's right. That's right. And I think that we already have seen significant success bringing together new people coding. Often these have been younger individuals, and some have had some experience, some have not. But we've seen the development of our first, what you might call a exercise, programming exercise. We call it the bird brain game, and there will be more. We're looking forward to doing the loss function and other more useful programs. So here, by building code sets together, as in separately as individuals, together as a team, we will demonstrate the working principles of Augment, which, like the commercial air flight and of the surgeon in software, in the production of software, we can use working principles to build very highly collaborative and effective teams, even with a green trainees in there, in the system. And we can make very good and economical, reliable, economical code sets that work with real systems and real businesses.
As we go forward into our next conversations, we're going to continue to draw upon stories and continue to pull out engineering principles as well as lessons for other parts of Augment training. What would you say, as now we're taking our trainees from high school and college students through the first parts of engineering principles, what would you say is the next step here?
One of the things that people find out when they learn to program is the code doesn't work as well as they had hoped, and the more lines of code they add, the less difficult, or the less success they have, the difficulty increases. And some of the concepts in regular engineering makes it easy for us to accomplish pretty complicated tasks. And we know about airplanes and buildings. There are a lot of things that we do very, very well. Televisions, the cell phones, etc. Very reliable, very economical. I mean, cell phones are one of the most complicated systems of technologies you can find anywhere. Mm-hmm. It's very small, but it's filled with an awful lot of various types of technology. Now, software doesn't appear to have complexity when you first start working with it. You put one piece, then another piece, then another piece. And what people do is they try to, in quote, test the software to see if it's working, test the code. Now, this word test is taken generally from other engineering areas. But other engineering, for example, if you have a bridge, you can't really test a bridge. You wouldn't want to, even if it were possible. So what an engineer does with a bridge is you have a mathematical model of the bridge. And by having the knowledge of how that mathematical model corresponds to the stresses in the bridge, if you have appropriate sensors in the bridge, you can map the math model and the stresses in the bridge and determine if the stresses in the bridge are as the math model predicted. So that is not testing a bridge, but when you talk about testing the model, it's much more accurate. So mechanical engineers, civil engineers test the model and see if the model is working as predicted, and the data from the bridge, or whatever it might be, the building, is the correct data. If the data corresponds to the predictions in the model, then we say that the bridge is good. But that's not testing the bridge, you're testing the model. In software, that idea of the model is much more difficult to come by. So one of the first lessons that I think is important, like with the coffee cup and with the brick and the rope, this is why we start with these words, to give full, rich meaning so people understand. When we say coffee cup, given our knowledge of the glaze, when we look at that, now we can say, gee, the coffee cup is more complicated than what we seem in the coffee cup. The key component is the glaze, and also how well the glaze is applied, the quality of the glaze, the temperature of that in which the glaze is fired. So the coffee cup has a complexity. The same with software. As we're developing code, and we are trained in developing code, there's training processes, there's concepts, there's special tooling, that when we put these together, we get a better idea of how well the code is likely to perform. And we don't really have a model that we can build, that we can test the model, but we can accumulate data. And, well, we can't talk about that, that's in another session. There are a number of things that we do, that when we do them, we look at the results, we look at the information, and we can find out essentially what parameters. The code, in effect, has behaviors similar to the behaviors of the bridge, but they're not rigorous, they're not rigorously available, to us. And we can, however, look at these parameters and find out if certain standards are met, and we have certain types of what are called tests. That word is ambiguous here, unit tests as it's called. There are things we can do when we assemble that information together using a modeling approach. Then we can say we have some information that our code is working as we expect it to, as we have trained the people. It's all dependent on the individual. And as prior work, prior art, enables us to see how well our code compares to others. And in software, it's about competition, price, performance. So we don't have absolute analytical means to determine the exact quality of software. What we can do is determine if our software quality and performance is significantly, notably, and demonstrably better than our competition. That's what we intend to do with the kind of a quasi-test model we would use in software. So engineering is about doing what you can with what you have, and doing a good job of it, and being able to show other people that you've done a good job. That's what Augment's about. We augment our capabilities of individuals, of the languages we use them to the best of our ability, and that language is capability, an important word, capability. And in doing so, we can show that we can compete very well with our competition. And that's what Augment is about, serving the customer well and having the best price performance that you're going to find in the marketplace. That is what your vision, Eric, is about. And I'm here to help in any way I can with my experience, as you have said. And it's a delight working with the often they're younger people in high school and in college. We're very much interested. And then as time goes on, we'll bring in older people, more experienced individuals, and all of this weaves our rope together and
Right.
makes for a much stronger organization. And with that, we will fulfill the vision that you had years ago. You're still young, but you've had this vision for some time. Impressive, and it's becoming more impressive as we go. At least we like to think that, and I think you're doing a good job.
I agree. I think it has become a lot more impressive, largely due to your experience applied to, again, a significant need, and that significant need is, in some ways, we might say, the transition from habits of mind and habits of software programming practice, which lead to poorer outcomes, and then transitioning those habits to new definitions for the word test, for example. That right there leads to predictably better outcomes for software development, which is one of the primary first things that our trainees need to understand, is this transition from defining a word perhaps wrong or too loosely to defining a word accurately and providing it with an area of validity, which is...
And we'll talk about that, operational definitions.
Right.
You can't define words with other words. It sounds surprising. You have to point at things. And software, it's often harder to do that, but we can. And that's what engineering is about, doing what you can with what you have, doing often more than what you thought you could do.
Right.
So I think this winds up this session,
Agreed.
and we might broadly talk about this session as about MPT, as I call it, methods, procedures, techniques, which is further about theory and hypotheses, physical laws, process, technology, and we will explain these terms more as we go, and show that the words all fit together, like the rope, like the brick. And that as we build a system with these concepts and as we understand them well, and as the people individually understand them, the organization performs better and better and better. It pulls together.
Yeah, and it performs as we would expect, meaning we have a model for how it should perform, and we know the parameters that will define its performance according to that model. Pleasure to have you here, Gary, working with us and the rest of the trainees, and looking forward to our next video.
Same here, Eric. Good to be here.